In the following lectures, we're going to now layer more information onto our idea of covalent bonding. We've talked about Lewis theory, and we've talked about its limitations and some exceptions, and then we've layered on VESPR theory to have an idea of the three-dimension picture that these molecules have in space. Now we're actually going to dive deeper, and it's going to involve saying, well, as great as Lewis and VESPR theory are, they don't really explain the behavior of molecules. They're not an accurate picture. And we said that. We said it was a bookkeeping method. We said it was a way to predict what the structure might look like. So we're going to now connect back to our idea of the electronic structure of an atom in a quantum atom and connect that to covalent bonding. So we're going to do this first with valence bond theory, and then we're going to introduce and discuss molecular orbital theory. And these are both theories that describe how covalent bonds arise. All right, so let's talk about bonding. Let's talk about what's happening in a covalent bond. Now, we've talked a little bit about reaction dynamics. We have things collide and they either separate or they collide and they form a molecule, but it's something new. But these bonds are really about orbitals that contain electrons coming together and overlapping. And when those orbitals overlap, the electrons in them can now be attracted to both of the nuclei of the two atoms that are forming the covalent bond. Now, a strong covalent bond is going to have a few requirements. It needs to have significant orbital overlap. So the more overlap that occurs, the stronger that bond is. It's really requiring those nuclei to come closer together, giving that electron that's shared the opportunity to be even more attracted to both of the nuclei because that distance is shorter. So the more overlap we have with our, and here, this is trying to show overlap right here. The more overlapping, kind of like a Venn diagram, that we see between these orbitals, the stronger the bond. But the other key part of this is the orientation at which these orbitals overlap. And so it's really important to have a strong covalent bond that they are aligned where head on. So they overlap directly. So rather than at an angle like this. So this would be a weaker covalent bond where we have our, and this one's stronger, where we have our orbitals that aren't perfectly aligned and they're kind of overlapping at an angle. And so we won't have as strong of a bond or connection between those two. So if covalent bonding is really just the overlap of orbitals, and we have a picture from when we talked about the electronic structure of the atom of what those orbitals look like, or the probability of an electron around the nucleus, what that kind of looks like, the shape of those orbitals in space. Which again, remember, an orbital is really the description of an electron as a wave function. That electron is in the probability of being in that space as a wave, and the space that it's not, those nodes, that's the inflection of a wave, right? Where it has zero probability of existing. So we're going to build on that idea and create, well, we not create, but we're going to build on that idea to have a deeper way of looking at covalent bonds called valence bond theory. So some of the reasons why we need to go deeper, why we need a different theory other than just Lewis theory, which can predict these structures, and then we can use VESPR theory to predict them in 3D, is that that prediction tool doesn't help us predict everything we want to predict about a molecule. So it doesn't accurately predict bond strength and bond length. We can't rely just on Lewis theory to say how short a bond will be or how strong a bond will be or how long and how weak. And it only approximates bond angles. They don't actually match up with what we see experimentally all the time. And so that's a problem. That's not a very powerful predictive tool if we have lots of exceptions that we see experimentally. We also see with Lewis theory that we cannot create a real accurate structure for a molecule that has resonance, right? We can create lots of structures and we can have a hybrid structure that gets closer to an idea of what we would see experimentally, but it's not a very clear picture of what's happening. So we need a better way of explaining resonance structures or molecules that have resonance structures, the bond lengths and strengths that they have. We can also see it doesn't consistently predict magnetic behavior. And we'll talk about magnetic behavior towards the end of this lecture series, about things being paramagnetic and diamagnetic, a little bit more in terms of how things bond. But going back to our electronic structure of the atom conversation, that magnetic behavior arises when you have unpaired electrons in orbitals. So that gives us our diamagnetic if everything is paired, or paramagnetic if we have unpaired electrons. So valence bond theory will be able to address most of these or all of these. And molecular orbital theory will address these as well. And so what valence bond theory states is that when orbitals of an atom interact to make a bond, they actually combine as hybridized atomic orbitals to form bonding orbitals. And so that hybridized bonding orbital, I guess, is really the key aspect of this entire theory. It means that a chemical bond is going to form from overlapping atomic orbitals within the atom. So those are our S, our P, and our D. And that the unpaired valence electrons in those SP or D, S or P orbitals would then spin pair and then become a little bit more stable in that overlapping orbital and create a bonding orbital. And so it's really about bringing those orbitals together. But we see that to be able to really create bonding orbitals that make sense with what we observe when we look at the 3D orientation of atoms around a central atom is that it's going to be more, well, we get a more stable arrangement when we look at hybridized orbitals rather than separate atomic orbitals only coming together. And so the geometries that we observe are going to be explained by this hybridization of atomic orbitals to build bonding orbitals. And these, this is key because the geometry of the overlapping orbitals is really what's going to determine that shape that we see in VESPR theory, where everything's going to try to repel and get far apart from one another. To be able to do that, we're going to have to hybridize our orbitals, our atomic orbitals, to create these new bonding orbitals. And that's valence bond theory in a nutshell.